tonight we're going to watch the moon do something you were never told to look for. Not shining, not changing phases, but leaving. You've grown up with this quiet picture in your head. You know the one. Earth and moon as a permanent pair, locked together in space like a logo, the same distance, the same relationship, forever. Because here's what nobody tells you. That scene is already out of date. The breakup has been happening your entire life. Right now, as you sit here, the moon is slipping away from us by about 3.8 centimeters every year. That's roughly the speed your fingernails grow, except this isn't biology. It's orbital mechanics. The moon looks frozen relative to Earth's face, tidally locked so that one hemisphere always stares straight at you. And yet, year after year, its orbit is very slowly inflating. So we have a paradox. From our point of view, the moon is the most stable object in the sky. Same side, same dance, same path. And at the same time, it is in the middle of a long, patient escape plan, spiraling outward into space. How can something look motionless and still be running away from us? This isn't a poetic metaphor. We've caught it in the act. During the Apollo missions, astronauts left mirror panels on the lunar surface. Today, we fired lasers from Earth, bounced them off those mirrors, and time how long the light takes to come back. Millimeter by millimeter, reflection by reflection, the distance grows. The data is brutally clear. The moon is not staying. So, let's start at the very beginning of your mental model. That classroom solar system poster, with the moon drawn as a neat little circle next to a flat blue Earth, like a permanent ornament. It feels safe. It feels fixed. But that picture hides a moving target. The distance between Earth and moon is changing right now while you watch this, while the real moon arcs over your roof. And here's the unnerving part. The thing pushing it away is not a rocket, not some mysterious dark force in deep space. It's something you already know and mostly ignore. Tides, gentle rises and falls of the ocean, shallow waves on the surface of a spinning planet. How could that possibly shove a 7.3 quintillion ton rock into a higher orbit and quietly stretch the length of our days? Because here's what nobody tells you about tides. They are not just water sloshing around on a globe. They're gravity trying to tear Earth and moon out of their current arrangement, trading rotational energy for orbital distance. And yet, something is above the planets. Something is below them. In this case, it's not up and down in the solar system. It's closer and farther in the Earth-Moon plane, and tides are slowly choosing farther. Now, let's begin a different way of seeing that pale circle in the sky. By the end of this journey, the moon won't just be a comforting nightlight. It will be a chapter in a long tidal story that rewrites Earth's past, stretches its future, and quietly turns our 24-hour day into something very different. So let's actually rewind that story, not with a time machine, but with a mental time lapse. Take the moon, you know the one, a neat white coin hanging over your neighborhood. Now imagine dragging a cosmic slider backwards, not for years or centuries, but for billions of years. The moon doesn't just move, it swells. It climbs toward us. Night after night in this rewind, it grows into a looming globe, many times larger in the sky than anything you've ever seen. Because here's what nobody tells you. The shrinking moon in our sky isn't a trick of poetry. It's geometry and gravity playing out in slow motion. Shortly after it formed, the moon may have been only a few Earth diameters away, perhaps 20 or then 30,000 kilometers out instead of almost 400,000. At that distance, it would have dominated the heavens, filling a huge chunk of your view, bright enough to cast shadows like a low-hanging lantern. Now, let's begin to mess with your sense of time. Spin the Earth in that same rewind. As the moon comes closer, Earth whips faster. A day is no longer 24 hours. It collapses. 5 hours. 6 hours. Sunrises and sunsets race past like a strobe. You'd barely finished lunch before it was night again. The 24-hour day you build your whole life around. That's not some cosmic default. It's a temporary truce between Earth's spin and the moon's pull. And those tides, they're not the gentle, predictable rises you watch at the beach. With the moon looming overhead, tides would have been far stronger, heaving entire coastlines, flooding vast areas, then draining them again. Imagine shallow seas sloshing in and out like a giant planetary lung. That constant rhythmic chaos reshapes shorelines, stirs nutrients, and carves tidal pools where early life can get trapped, stressed, and forced to adapt. Stronger tides mean stronger mixing of ocean and atmosphere, which means climate and chemistry are different too. This isn't just scenery, it's the background engine for evolution. So what's the paradox we're really living inside? The moon is stealing Earth's spin and paying it back as distance. Our fast rotation rubs against the oceans. Tidal bulges lag behind. And friction turns spin into heat, while gravity throws a tiny bit of that stolen momentum into the moon's orbit. Earth slows. The moon drifts. It's a slow-motion getaway, powered by our own rotation. And yet something is above the planets. Something is below them. In this Earth-Moon system, above is farther out in orbit, and the moon is climbing that invisible plane 1 centimeter at a time. How do we know this isn't just a nice story? Because we've literally caught the moon in the act. We left mirror panels on its surface during Apollo, and today we fire lasers at them from Earth. The light goes up, bounces off, and comes back, letting us time the round trip to the millimeter. Those measurements say the moon is slipping away by about 3.8 centimeters per year. But that clean number hides a much messier past. How fast was it moving away when days were only 5 hours long? What do ancient rocks and fossil corals remember about that alien rhythm of tides and sunlight? To answer that, we have to read the scars in Earth's crust and the growth rings of long-dead creatures and see if they agree with the lasers. That's where the tidy picture breaks and the real detective story begins. That detective story is where this gets fun, and this is where you come in. If the idea that the moon is quietly stretching our days, stealing our spin, and very slowly escaping into space is tugging at your brain right now, that's not an accident. Your curiosity is the reason we get to make videos like this at all. So before we peel back the next layer of this orbit puzzle, we need to make a tiny deal with you. We're going to keep this video focused on the story and the science. No endless sponsor tangents. No 5 interruptions begging you to click things. Because here's what nobody tells you. Your smallest actions on a video like this are weirdly powerful. A like, a quick subscribe, or a one-line comment can push this whole conversation about tides and gravity into the feeds of people who still think the moon just sits there. So here's the low-effort, high-impact challenge. In a second, we're going to ask you to pause. Before you hear the answer from fossils and lasers, take your best shot. How long do you think one day was when dinosaurs walked under the moon? Not now, not in the early 5-hour day chaos, but during that Jurassic and Cretaceous world. You know, the one from every childhood poster and documentary. Pattern interrupt time. Don't overthink it. Pick a number of hours. 20, 22, 30? Type it into the comments right now with just a few words. My guess for dinosaur day length, X hours. Then hit play again. Future you gets to scroll back later and see how close you were. And future us gets to see how your intuition about Earth's spin actually lines up with the geological record. So, let's start at the very beginning of this little pact. You give the video a quick boost with a like or a sub. You drop that guess in the comments. And in return, we'll keep delivering a clean, distraction-free dive into what the moon is really doing to our planet. No fluff, no detours, just a sharper picture of a relationship that has been shaping every sunrise you've ever seen. Now let's begin the real reconstruction, because once we're on the same page, we can rebuild our mental model of the Earth-Moon system from the ground up. Not as a flat diagram with a polite gray circle, but as two worlds locked in a slow exchange of energy, trading spin for distance. And yet something is above the planets. Something is below them. The same gravity that sculpts the grand planes of the solar system is also raising tides in your oceans and nudging the moon higher in its orbit. With our deal in place, it's time to watch that invisible handshake in motion. To really see that handshake, we have to step back to the picture you grew up with. You know the one. A blue marble for Earth, a smaller gray marble for the moon, and a perfect white ring looping around it like a halo drawn by a very patient compass. In that textbook picture, everything feels calm. The orbit is a clean circle, the distance is stamped in neat numbers, and the arrows are frozen like traffic signs in space. Orbital period, 27 days. Average distance, 384,400 kilometers. It's all so tidy that your brain quietly fills in the missing line. This never changes. So, let's start at the very beginning with that flat diagram pinned to the page. Earth sits in the middle, not wobbling, not flexing, just a round blue icon. The moon glides around it on a single unbroken track, as if someone laid a tiny model train rail in the plane of the solar system and pressed play. No spirals, no drift, just a month-long lap, forever. Because here's what nobody tells you. That picture is less a photograph and more a logo. It's a brand mark for how orbits work that quietly edits out anything messy or time-dependent. The distance label looks like a law of nature, not an average that only exists because the real orbit is slightly squashed and always shifting. Think about the way we memorize the basics. The moon is tidally locked, so the same face always points toward you. It takes about a month to orbit, so calendars and phases line up in this comforting rhythm. It's about 384,400 kilometers away, so you can quote that number in a quiz and feel like the system is nailed down, fixed, solved. In your head, it turns into a toy. Two balls on a string, whirling around a common center that never moves, like a perfect playground experiment. You spin them. They keep going. The spacing never changes. No energy is lost. No orbits swell or shrink. It's orbital clockwork, ticking in the dark. And the diagrams lean into that feeling. The arrows showing direction never bend. The 27-day period never stretches. Even the word locked, intidally locked, sounds like someone threw a cosmic deadbolt and walked away. Why would you ever suspect that anything is still evolving here? Yet hidden under that calm is a slow imbalance. Gravity is tugging. Oceans are sloshing, and friction is quietly stealing energy from Earth's spin. The logo doesn't show that. The string between the two balls isn't perfectly rigid after all. It's more like a very slow, invisible winch. Hold that static, balanced, almost clockwork's picture in your mind. Because in the next part, we're going to press unpause on it and watch what actually happens when you let this system run for millions of years instead of a single tidy diagram. So here's the twist. That tidy picture you're holding in your mind, the one with a crisp white circle for the moon's path around Earth, labeled with a single distance and a single orbital period, it isn't exactly wrong, but it quietly deletes the most important thing that's happening, because here's what nobody tells you. When we draw a fixed ring and stamp 384,400 kilometers next to it, we're not just simplifying. We're training your intuition. Fixed circle, fixed number, fixed arrows for gravity. Your brain does what all of our brains do. It assumes this is a permanent layout, a kind of celestial logo that never really changes. You know the one. Earth in the middle, moon going around like a second hand on a clock, everything looping along the same track forever. It feels safe, mechanical, almost boring. And yet something is above the planets. Something is below them. Time. If you could hover in space for millions of years and watch that picture on fast forward, the moon wouldn't politely retrace one neat ring. You'd see a slow spiral, the path uncoiling outward, lap after lap, like a record that's slipping toward a larger groove. That's the part the flat diagram hides. It freezes the Earth-Moon system as if nothing important is leaking away, as if this is an isolated, frictionless pair of gears. But Earth is not a polished machine in a vacuum. It's covered in oceans that slosh, crash, and drag against the seafloor. Its crust flexes under those tides, heating and creaking. All of that motion is rubbing down Earth's spin and feeding energy into the moon's orbit. So the real hidden assumption in that classroom picture is brutal simplicity. No friction, no tides, no losses. In that fantasy, Earth can spin forever at the same speed, and the moon can circle forever at the same distance. In reality, every tide is a tiny transaction. A little bit of Earth's rotation gets cashed out as heat in the oceans and rock, and a little bit gets wired into the moon's motion, nudging it farther away. Does that feel like a clock to you, or more like a very slow, creaking machine? Now let's begin to swap mental models. Don't think of Earth and Moon as perfect gears turning in a timeless logo. Think of them as parts in an ancient winch, with Earth's spin on one side and the Moon's distance on the other. Turn one down, and the other ratchets up, one tide at a time. Because once you see it that way, the question stops being, why is the moon moving away? And becomes, how fast is the winch running, and how far can it go? So let's test that winch. Not on a chalkboard. From a front row seat. Now let's begin with you on a silent observation deck, inside a ship parked high above Earth. No atmosphere, no clouds, just the planet turning below and the moon sliding around it. We give you a time-lapse dial and tell you to crank it. Not to next week, to the next million years. You turn the dial. Days blur into streaks of blue and white as Earth spins faster than your eyes can track. The moon's orbit becomes a glowing ring, then something strange happens. That ring is not quite a ring. It starts to breathe. With every lap, the circle swells outward by the tiniest amount, tracing a slow, widening spiral in space. Because here's what nobody tells you. The moon isn't just going around. It's climbing away. Each orbit on average ends about 3.8 centimeters farther out than the last. That's less than your fingernails grow in a month. If you watched in real time, you would see nothing. Not this year, not in your entire life, but in your million-year time lapse. The pattern is undeniable. The spiral thickens. Its loops no longer perfectly stacked. The moon's orbit, which your schoolbook pictured as a neat, flat oval, now looks like a slowly expanding coil, lifting away from Earth's gravity, well, 1 millimeter of energy at a time. And yet, something is above the planets. Something is below them. In this little two-body system, the above is the future path of the moon. The below is where it used to be. Watch Earth while this happens. At the start of your movie, it's spinning just a bit faster. The continents smear into bands. The oceans whip around, tides racing ahead of the moon. As time speeds up, those tides drag against the seafloor, turning our rotational energy into heat and flinging angular momentum into the moon's orbit. Earth's spin slows. The moon's orbit swells. The winch turns. So, let's start at the very beginning of your intuition. You're used to thinking of orbits as closed loops, as if the solar system were a clock that repeats itself forever. But from this vantage point, you see that an orbit can also be a path through time, a spiral that records every tiny trade between spin and distance. One shorter day on Earth here, one slightly wider orbit there. On human scales, this is invisible. On geological scales, it's brutal. Give the spiral 1 billion years, and the moon retreats hundreds of thousands of kilometers. Give it 4 billion, and our companion migrates from a looming giant in the sky to the modest disk you know today. And that raises a bigger question. If this spiral has been running for billions of years, where did it start? And what did Earth look like when the moon was still near the center of the coil? That spiral isn't just a pretty picture. It hides the real mystery we're chasing in this video. The moon is moving away from Earth, about 3.8 centimeters every year. That's a hard, measured fact, not a poetic metaphor about growing apart. So what we're really asking is threefold. Why is it moving? How do we actually know that? And what does this slow escape mean for Earth's past and future? Because here's what nobody tells you. Once you pull on that thread, you end up unraveling the length of a day, the shape of our tides, and the conditions that let complex life settle down here in the first place. So, let's start at the very beginning. Before we talk about tides and lasers and fossil corals, we need the origin story of this whole Earth-Moon system. Not the neat, flat diagram where you just drop a moon into orbit and call it a night, but the violent collision, the molten debris cloud, and the newborn moon that once orbited so close it would have filled half the sky. What did nights look like when the moon was only tens of thousands of kilometers away and racing around the Earth in a matter of hours? If you could stand on that early coastline, would the horizon feel stable at all? Or would the sky itself seem to heave under the pull of that giant companion? Once we've set that scene, we'll move to the engine that keeps the spiral turning, tides and energy transfer. How does a bulge of water on a rotating planet, dragged forward by friction, actually push a whole moon higher in its orbit? Why does the same process quietly rob Earth of rotational energy, stretching our days from 5 hours to 24 and beyond? In space, there is no up, there's no down, and yet something is above the planets. Something is below them. In the same way, nothing is literally pushing the moon, and yet gravity and friction are trading energy in a way that behaves exactly like a hidden engine. Then we'll ask the uncomfortable question: how do we know any of this isn't just a clever story? This is where we bring in the receipts. Laser beams bouncing off retroreflectors left by Apollo, catching the moons in the act of drifting away, millimeter by millimeter. Ancient corals and tidal rhythmites that record more than 400 days in a year, and shorter, frantic spins of the young Earth. What happens to eclipses as that distance grows? Will there be a time when total solar eclipses simply stop. By the end, you won't see the moon as a fixed ornament hung in a flat orbit. You'll see a relationship that has been evolving for 4.5 billion years. A slow-motion dance that gave us familiar tides, 24-hour days, and a remarkably stable stage for life. Now let's begin. So, let's start at the very beginning. If the moon is slowly leaving, we have to ask a much harsher question first. How did it get here at all? Roll the clock back 4.5 billion years. The solar system is not a calm, flat diagram yet. It's a demolition derby. The sun has formed, the planets are still assembling, and Earth is more work in progress than world. You're looking at a molten, half-finished planet being hammered by leftover building blocks, from pebbles to mountain-sized bodies, all falling in under gravity from every direction. Now picture something bigger, much bigger. The leading idea is that there was another world in our neighborhood, roughly the size of Mars. You know the one. It even has a name, Theia. It didn't politely miss us. It hit us. Not head-on, but in a glancing, catastrophic blow that makes every asteroid movie you've ever seen look like a gentle nudge. Because here's what nobody tells you. That one impact didn't just scar Earth. It reset the entire Earth-Moon system before it even existed. In a few brutal hours, the outer layers of both worlds were shredded, vaporized, and hurled into orbit. Rock turned to vapor. Oceans of magma splashed into space. Around the ruined proto-Earth, a hot, glowing halo of debris wrapped itself into a thick disk, like a miniature version of the protoplanetary cloud that once circled the young sun. This wasn't a peaceful ring. It was chaos and fast forward. Inside that disk, fragments smashed together, melted and merged over and over as gravity tried to turn a spray of orbiting rubble into a single companion. Imagine looking up from the blasted surface of early Earth and seeing not one moon, but a blazing, churning ring of incandescent rock stretching across the whole sky. Night? Not really a thing yet. Out of that disk, the moon condensed. It cooled from a glowing ball of magma into a solidifying world. But here's the key for our story. It started off close, ridiculously close. Instead of today's 384,000 kilometers, the newborn moon probably orbited only 20 to 30,000 kilometers away. That's closer than some of our modern satellites. In the sky, it would have loomed several times larger than the full moon you know. And that closeness changes everything. A nearby moon means savage tides, not the gentle rise and fall you see at the beach. Whole oceans sloshed with each orbit, flexing Earth's crust, turning rotational energy into heat and yanking on the moon's path. From the very first orbits, Earth's spin and the moon's orbit were locked into a tug of war. And yet, something is above the planets. Something is below them. In this case, it's not about a flat plane in space. It's about how that early, lopsided Earth-Moon dance set the direction for everything that followed. Those extreme tides were the opening move in a long game of energy exchange that would slowly push the moon away. So if one impact lit the fuse, how exactly does that hidden mechanism work today, centimeter by centimeter? To answer that, we have to zoom in on tides, friction, and why the same lunar face always looks back at you. Now let's begin by doing something wild. Take the world you know, slow blue oceans and a 24-hour spin, and just speed it up until the whole planet is a blur. Early Earth wasn't taking its time. A day could be over in 5 or 6 hours. The sun would rocket from horizon to horizon, so fast you could almost watch the shadows move in real time. Morning, noon, and night would chase each other around the globe like they were late for an appointment. You know the one. That calm, predictable sky we take for granted, erase it. Because here's what nobody tells you when you see that neat diagram of the Earth-Moon system. Right after the impact, the moon wasn't a polite little coin hanging in distant space. It was a monster. It may have hovered only a few Earth diameters away, so in the sky it would have looked several times larger than today. A swollen, glowing wound of half-cooled rock dominating everything. Picture standing on that young world, if you could stand at all. The moon rises huge, racing upward, its orbit so tight that it appears to climb and fall far faster than you're used to. It doesn't just drift, it sweeps. In just a few hours, the whole scene changes, because Earth is spinning like a skater pulling in their arms, and the moon is whipping around in a close, precarious orbit. Down on the surface, gravity is having a field day. That enormous nearby moon is yanking on Earth's oceans, and even on its still molten interior. Tides aren't gentle ripples, they're planetary scale pulses. You'd see walls of water and bulges of magma hundreds of times stronger than the tides we know, sloshing around the globe with every frantic spin. Coastlines wouldn't just flood, they would be erased and redrawn, over and over. And yet something is above the planets. Something is below them. In this case, those somethings are the gigantic tidal bulges Earth is trying to carry along faster than the moon can keep up. The planet's rapid rotation drags those bulges slightly ahead of the line connecting Earth's center to the moon. That tiny offset is everything. Now the friction kicks in. Ocean water grinding against the seafloor, molten rock shearing against deeper layers. All of it converts rotational energy into heat. Earth is literally breaking on its own tides. At the same time, gravity between the off-center bulges, and the moon tugs the moon forward in its orbit, handing it energy, pushing it outward. So from this chaos, a 5-hour day, a monster moon, and ferocious tides, you get a built-in engine that must slow Earth down and push the moon away. But how do you go from that extreme, roaring system to the quiet 24-hour rhythm and modest tides you know now? And how do we measure that ancient slowdown using corals, rocks, and lasers fired across space? That's where the real detective story begins. So from that roaring beginning, something surprising happens. The Earth-Moon system calms down. Not instantly, not neatly, but it starts trading chaos for rhythm. Because here's what nobody tells you. Once the debris settles and the magma oceans cool a bit, you don't just have a random rock and a random moon. You have a connected machine, locked together by gravity and by a shared budget of spin and motion that it can't easily escape. Now, let's begin with that budget. Physicists give it a fancy name, angular momentum. Think of it as all the spinning and all the orbiting added up. Earth's rotation is part of it. The moon's orbit is part of it. Together they form one combined account, and in the absence of big external kicks, the total in that account stays almost the same. But there's a twist. The total is nearly conserved, yes, yet it can be shuffled around inside the system. Faster Earth, slower moon, slower Earth, faster moon. You know the one. It's like two ice skaters holding hands, pulling and pushing so one speeds up while the other slows down, but their shared motion is still balanced overall. Right after the impact, Earth was spinning wildly, a day only a few hours long, while the newborn moon whipped around in a stretched, eccentric path, much closer than today. Over millions of years, gravity kept tugging on the high points of that orbit, draining away the most extreme motions and smoothing them out. The moon's path gradually circularized, turning from a lopsided loop into something more like the nearly round orbit you'd recognize in a textbook picture. At the same time, the orbit tilted, not by a dramatic 90 degrees, but by a modest few degrees relative to Earth's equatorial plane and the plane of Earth's path around the Sun. That slight tilt is a fossil of the messy beginning, a reminder that even when a system looks neat and flat, the scars of its violent origin are still written into the angles. Meanwhile, Earth's frantic spin started to ease. Each rotation stretched the young oceans into huge tidal bulges, and those bulges did not line up perfectly with the line to the moon. Friction with the seafloor and continents turned some of that spinning energy into heat, and the spin plus orbit budget quietly rebalanced. And yet something is above the planets. Something is below them. In our local case, that above and below becomes earlier and later. A fast-spinning early Earth, a slower present Earth, and a moon that has traded closeness for distance. All of this sets up the central act of our story, a cosmic tug of war where tides act like a brake on Earth and a gentle push on the moon. How does that invisible hand actually work? And how do we catch it in the act with corals, rocks, and lasers across space? That's the engine we're about to open up. So we've opened the hood on this cosmic engine. Now we need to look at its first big word consequence, the moon's frozen face. You know the one. That familiar pattern of dark Maria and bright highlands that every child's drawing of the moon quietly assumes is the only side it has. In reality, the moon is a full sphere spinning in space. So why does it behave like a spotlight that never swivels, always aimed straight at Earth? Why don't we ever see the far side without a spacecraft sneaking around the back? Because here's what nobody tells you. The moon absolutely does rotate. It just rotates in perfect lockstep with its orbit. This is tidal locking. The moon takes about 27 days to go once around Earth, and it also takes about 27 days to spin once on its axis. One spin per orbit. That's the trick. Imagine you and a partner on a dance floor. You walk in a slow circle around them, but you keep your face pointed toward theirs the whole time. By the time you've completed one lap, you've also completed one full turn. That's the moon's dance, written into rock. But the moon didn't start out as that polite dancer. Early on, fresh from the impact that formed it, it was spinning much faster. Picture a hot, molten world whirling inside Earth's gravity field. That uneven pull raised tidal bulges, not in oceans, but in the moon's solid rock, stretching it slightly along the Earth-Moon line. Those bulges couldn't instantly keep up with the spin, so they were dragged out of alignment. And when gravity pulls on something that's out of alignment, it does work. Inside the moon, those shifting bulges flex the crust and mantle, creating internal friction. Friction turned rotational energy into heat, like bending a metal coat hanger back and forth until it warms in your fingers. Bit by bit, rotation energy leaked away as heat, and the moon's spin slowed. Eventually, the rotation period lengthened until it matched the orbital period. One face always pointed toward Earth, the bulges lined up, and the internal grinding dropped to a minimum. The system had found a stable configuration. Lock achieved. From the moon's point of view, Earth now hangs almost fixed in its sky. So, let's start at the very beginning of the bigger picture this sets up. If tides can grab an entire world and break its spin until it locks, what are they doing to a much larger, faster spinning planet covered in deep oceans? And yet, something is above the planets. Something is below them. The same invisible tides that froze the moon's face are quietly reshaping Earth's rotation and the moon's orbit. trading day length for distance. That's the deeper trade we're about to watch in slow motion. So if tides can lock an entire world and break its spin, we need to be very clear on what a tide actually is. Because here's what nobody tells you. It's not just those waves you see rolling up the beach. Those are mostly wind. Tides are something slower, deeper, and much more global. Now let's begin with the picture in your head. You know the one, the classic shoreline view. Waves marching in, surfers waiting, the water sloshing back and forth every few seconds. Those fast ripples are like wrinkles on a coat. A true tide is the coat itself being stretched ever so slightly by gravity. It's not just the ocean's surface that moves. The entire earth flexes. So let's start at the very beginning. The moon's gravity doesn't grab every part of Earth equally. The side of Earth facing the moon feels a slightly stronger pull. The far side feels a slightly weaker pull. That difference, that gradient in gravity across Earth's diameter, tries to stretch our planet along the line connecting Earth and Moon. If you could strip away the continents and watch from space, Earth would look very subtly like a squashed sphere pulled into a rugby ball. That stretching creates not one, but two main tidal bulges. One bulge faces the moon, where the ocean is pulled a little closer. The other bulge sits on the opposite side, where the water is, in a sense, left slightly behind as the rest of Earth is pulled more strongly. It feels backwards the first time you hear it. High tide under the moon and high tide directly opposite the moon at the same time. That's the paradox built into the word tide. As Earth spins, you rotate through those bulges. They don't pop in and out of existence like a light switch. They're more like slow-motion hills of water and flexed rock that Earth's surface keeps sliding under. In deep ocean, the bulges can be hundreds of kilometers wide, quietly moving across basins, wrapping around continents, reflecting off coastlines. The crust itself rises and falls by tens of centimeters under this pull. You're riding that vertical motion right now. And the moon isn't working alone. The sun also raises tides on Earth with its own pair of bulges. But the moon is so much closer that its tidal gravity wins. It's roughly twice as effective as the sun's, which is why the moon is the main player in our story. Together they create spring tides, neap tides, and a constantly shifting pattern that coastal communities live by. Here's the twist. Those migrating bulges aren't frictionless. As they drag across ocean floors and scrape past continental shelves, they turn organized motion into heat. That invisible braking is the engine that trades Earth's spin for the moon's escape. And in the next section, we'll watch how that trade actually happens. That invisible braking doesn't just warm the oceans and the seafloor. It twists the entire Earth-Moon system into a strange gravitational tug-of-war that quietly shoves the moon outward. Here's the key move. Earth spins once every 24 hours, but the moon takes about 27 days to complete one orbit. Our planet is rotating much faster than the moon is circling us. Because of that, the tidal bulge that the moon raises in our oceans doesn't sit politely underneath it. It gets dragged ahead, pulled a little in front of the moon's position in its orbit. Picture a spinning water balloon with a heavy weight orbiting around it. The weight tries to pull a bulge of water directly toward itself, but the balloon is spinning so fast that the bulge is yanked forward, like it's being carried along by the spin. Because here's what nobody tells you. That tiny offset, just a few degrees, is where all the action is. So let's start at the very beginning of this interaction. The moon's gravity is trying to line the bulge up with itself. Earth's rotation is trying to drag the bulge ahead. Those two tendencies don't match, so you get a constant torque, a twisting force, as if the moon has grabbed a gravitational handle on Earth's oceans and is trying to pull them back into alignment while Earth insists on spinning ahead. Now flip the picture. That misaligned bulge has its own gravity because it's slightly ahead of the moon along its orbit. Its pull on the moon isn't straight inward, it's tilted. Part of that pull is forward in the direction the moon is already moving. With every orbit, that forward component acts like a tiny, repeated nudge, the same way you'd push a child on a swing at just the right moment to make the arc a little higher. And in orbital mechanics, a forward tug is everything. Add a little speed at just the right point, and you don't make the moon crash into us. You make its path wider. That extra energy lifts it into a slightly higher orbit, where it circles more slowly and sits a little farther away. Do this for billions of years, and those millimeters per day turn into centimeters per year, and eventually hundreds of thousands of kilometers of separation. So the moon is quietly gaining orbital energy, climbing the gravitational hill and slipping away into space. You know, the one question this raises next: if the moon is getting that energy for free, where is it really coming from? And what exactly is Earth giving up in the trade? It feels like a magic trick. The moon drifts away, gains energy, and we didn't plug in any cosmic battery. Because here's what nobody tells you. The power source is right under your feet. Earth is literally paying for the moon's escape with its own spin. So, let's start at the very beginning of that trade. Right now, Earth is rotating faster than the moon is orbiting. A point on the equator whips around at about 1,600 kilometers per hour, while the moon takes about 27 days to go once around its orbit. That mismatch matters. It means the tidal bulge we talked about doesn't line up neatly under the moon. It gets dragged ahead, pulled forward by Earth's faster rotation. That misaligned bulge is where the price gets paid. As the oceans slosh around, they aren't sliding over a perfectly smooth marble. They're being dragged across a very not flat seafloor, up against continental shelves, squeezed through narrow bays. Every time a tide rushes in and out, friction rubs on the ocean bottom and the crust. That rubbing converts some of Earth's rotational energy into heat. Tiny, everywhere, all the time. You can think of it as the planet's spin slowly being bled off into the oceans as a very gentle, global break. But not all of that energy becomes heat. The misaligned tidal bulge is also being tugged back toward the moon by gravity. Because the bulge is slightly ahead of the moon in its orbit, its gravity pulls the moon forward, like giving a skateboarder a push at just the right moment. A forward pull in orbit means more orbital energy. More orbital energy means a higher, wider path around Earth. Now, let's begin the skating lesson version. Picture a figure skater spinning alone in the center of the rink. You know the one, arms tucked in, spinning fast. Now they grab a partner's hands and fling that partner outward into a wide circle. As the partner speeds around, the original skater's spin slows down. They've transferred some of their rotational energy and angular momentum into the partner's bigger orbit. Earth is that central skater. The moon is the partner being flung outward. The key is that the total angular momentum of the Earth-Moon system stays almost constant. The accounting has to balance. As Earth loses spin angular momentum, the moon gains orbital angular momentum. As Earth's rotation energy is partly turned into heat, the rest shows up as the moon's higher orbit. So the trade is simple, but dramatic. Earth's days get longer. The moon's orbit gets larger. The whole Earth-Moon picture slowly stretches. And yet something is above the planets. Something is below them. Because this tiny tidal energy exchange doesn't just reshape our month and our day, it plugs the Earth-Moon system into the larger rules of gravity and motion that shape the entire solar system. Which raises a deeper question. If this process has been running for billions of years, how different were Earth's days and the moon's sky-filling presence in the deep past? To answer that, we have to look down, not at the moon, but at the moving skin of water wrapped around our planet. Those two tidal bulges you picture, neatly opposite each other, gliding around a smooth blue sphere, you know the one. In reality, they're trying to move like that, pulled by the moon's gravity into a simple, clean orbit around Earth's axis. But Earth isn't a smooth global bathtub. It's a lumpy world with continents, island chains, narrow bays, and ocean basins that are all the wrong shapes and depths for a graceful sliding tide. Because here's what nobody tells you. Most of the tidal energy isn't in those pretty diagrams. It's in the chaos. As the planet spins under the moon, water is forced into and out of long, shallow shelves like the North Sea, squeezed through narrow channels like the Bay of Fundy, and made to climb over rough seafloor ridges and submarine mountains that would put the Rockies to shame. The bulge wants to lead the moon, pulled ahead by Earth's fast rotation. The continents say, not so fast. Coastlines reflect waves back, bays amplify them, and shallow seas slow them down. In some places, high tide arrives hours late compared to the simple geometric picture because the water has to slosh, resonate, and fight its way around corners first. Every time a tidal wave breaks against a cliff, every time a current shears over a jagged seafloor, turbulence turns organized motion into microscopic whirlpools and heat. It's like dragging a giant, wet brake pad around the spinning planet. The oceans are trying to move in one smooth direction. The solid Earth is trying to spin underneath. Friction between them steals a tiny bit of rotational energy on each pass. And it's not just the water. The rock itself flexes. Under the moon's pull, continents rise and fall by tens of centimeters. The mantle slowly kneads, and even the deep interior feels a rhythmic squeeze. That flexing isn't perfectly elastic. Grains rub, faults creep, minerals deform and warm up. Hidden inside the crust and mantle, there's another layer of tidal friction, another subtle break on Earth's spin. From one day to the next, this effect is ridiculously small. You won't notice tomorrow being a microsecond longer. But let it run, uninterrupted, for millions of years, and that constant drag stretches Earth's day from 22 hours to 24 and beyond. Over billions of years, it has quietly retimed the rhythm of sunrise itself. So if this planetary brake pedal has been pressed for so long, does it leave scars we can still read? Are there rocks, fossils, entire coastlines that remember shorter days and a closer, brighter moon? And can they prove that this invisible braking really happened? Yes, the planet does keep a diary, but it's not written in ink. It's written in skeletons and sand. Now let's begin with one of the strangest clocks nature ever built. Some ancient corals don't just grow. They lay down microscopic daily bands, like tree rings and fast forward. Every sunrise, a thin layer. Every sunset, another. Stack those up for a year and you don't just get a fossil, you get a calendar. Because here's what nobody tells you. You can literally count how many days used to fit into one ancient year. Imagine slicing through a 620 million-year-old Coral colony, the way you'd slice through a layered cake. Under a microscope, you see bundles of bands grouped together. Within each bundle, about 400 tiny daily layers. Wrapped around that bundle, a thicker seasonal pattern that repeats once per year. So the coral is quietly shouting at us across deep time. In Moog Ocean, 1 year had roughly 400 days. Same Earth, same orbit around the sun, but more days packed into that orbit means each day was shorter. Do the math, and you get a day length of about 21.9 hours. The planet was spinning faster. Sunrises came sooner. Tides raced around the globe a little more quickly, and that invisible break from the moon hadn't slowed the rotation as much as it has now. You know the one. The mental picture where fossils are just old bones on a shelf. Corals blow that up. They're precision instruments, frozen mid-measurement, telling us that Earth's rotation really has been changing. But corals aren't the only witnesses. Some coastlines keep tidal journals. Enter tidal rhythmites. These are layered sediments laid down in shallow seas and estuaries, where tides slosh in and out. Each tide leaves a thin layer of mud or sand. Spring tides, when the sun, moon, and earth line up, carve thicker layers. Neap tides, when they're offset, leave thinner ones. Over months and years, you get a repeating pattern. Thick, thin, thin, thick, like a barcode written by gravity. So, let's start at the very beginning of how we read them. Count how many daily layers fall between two spring tide peaks, and you recover the timing of the tidal cycle. Count how many of those tidal cycles add up to a year, and you recover how many days fit into that year. Different rocks, different continents, different ages. And yet, something is above the planets. Something is below them. Two totally independent records both say the same thing. Ancient Earth spun faster, and the moon orbited closer. Corals, rhythmites, separate clocks, same story. Earth's rotation has been slowing, and the moon's orbit has been quietly adjusting in response. Remember that guess you made earlier about dinosaur-era days? Hold on to it. Because very soon, we're going to put that number side by side with what these fossil clocks and some very modern lasers say really happened. So we've got these ancient coral clocks and muddy tidal pages all whispering the same thing. Earth's spin is slowing. The moon is slipping away. But fossils are still circumstantial evidence. What if we could catch the moon in the act, in real time, with a stopwatch? Now let's begin with one of the strangest legacies of the Apollo era. When astronauts bounced around on that gray powder, they didn't just plant flags and grab rocks. They bolted down glittering panels made of tiny cube corner mirrors, called retroreflectors. You know the one. It looks like a flat metal tray, but each little glass cube is machined so that any light that hits it is sent straight back to where it came from. Because here's what nobody tells you. Those mirrors weren't a publicity stunt. They were the start of a decades-long experiment to measure the Earth-Moon distance with absurd precision. Not kilometers, not meters, millimeters. Here's how it works. On clear nights, a few observatories on Earth aim powerful green lasers at the spot on the moon where those Apollo retroreflectors sit. They fire a brief pulse of light into space and then wait, staring at the exact same patch of sky. 2.5 seconds later, if they're lucky, a handful of photons come whispering back, bounced off those tiny mirrors. The round trip takes about 2.5 seconds because light is fast, but the moon is far. So scientists time that journey down to fractions of a nanosecond. A nanosecond is a billionth of a second. Light only travels about 30 centimeters in that time. So if you can tell whether the pulse came back a tenth of a nanosecond earlier or later, you're sensitive to changes of only a few centimeters in the Earth-Moon distance. It sounds almost ridiculous. Fire a laser at a moving target 384,000 kilometers away, catch a few returning photons out of trillions, and use that to track an orbit. And yet, something is above the planets. Something is below them. In this case, it's a thin beam of light, arcing up from Earth's surface and down onto a dusty reflector, tracing out the invisible geometry of gravity between our worlds. So, let's start at the very beginning of the data record. The first successful lunar laser ranging measurements in the late 1960s gave us a baseline distance. Then we kept shooting, night after night, year after year, decade after decade. When you line up all those timings, a pattern pops out. The moon is not holding steady. The numbers drift, slowly, relentlessly. On average, the moon is receding at about 3.8 centimeters per year. That's roughly the rate your fingernails grow. Tiny on human scales, enormous on geological ones. And crucially, it's exactly what tidal theory predicts from Earth's loss of rotational energy. We have literally bounced light off the moon and watched it creep away. Not as a thought experiment, but as a measurement you can plot. A slow motion breakup, unfolding millimeter by millimeter. Which raises a bigger question. If we can see the moon leaving right now, how far has it already gone? And how much farther can it get before gravity calls a truce? To feel what that actually means, we have to zoom way in, because 3.8 centimeters per year sounds like nothing. It sounds like rounding error, but in human terms, that's about how fast your fingernails grow. If you could somehow hold your hand up next to the moon's orbit, each year the gap between Earth and the moon would widen by about the width of one of your fingers. Slow, gentle, almost tender, and yet, year after year, century after century, that tiny drift never stops. Now let's begin to stack those years. At 3.8 centimeters per year, you get roughly 38 kilometers every million years. That's like moving the moon an entire city's width farther out, just while life on Earth is busy evolving new shells, new eyes, new ways to breathe. Give it 100 million years, and you're talking thousands of kilometers. Give it several hundred million, and you're adding tens of thousands of kilometers to the Earth-Moon distance. Because here's what nobody tells you. The cosmos runs on compound interest. Small changes in orbit, repeated over absurd stretches of time, quietly rewrite the whole picture. And the moon isn't the only thing changing. Our clocks are too. Precision atomic clocks on Earth, compared with the timing of ancient eclipses recorded by astronomers and scribes, show that our planet's rotation is slowing. Your day today is longer than a day 100 years ago by about 1.7 milliseconds. That's not much. You will not be late to work because the planet took an extra 0.17 seconds to spin. But stretch that out over millions of years, and those milliseconds pile up into real, measurable hours. Fossil corals, for example, lay down daily growth bands. When we count those bands inside 1 year's seasonal cycle, corals from about 620 million years ago show roughly 400 days in a year. Same orbit around the sun, same year length in space, but more shorter days. Each day was only about 21.9 hours long. So the fossils, the eclipse records, the atomic clocks, the laser ranging, they all point in the same direction. The moon is receding, Earth is spinning down, and yet something is above the planets. Something is below them. In this case, it's deep time, sitting above and below our brief human lives, turning millimeters into continents of change. But there's a twist. The modern rate, 3.8 centimeters per year, and and 1.7 milliseconds per century lines up with that long, gradual story, yet it can't have been perfectly constant. Ocean shapes shift, continents move, ice caps grow and melt. All of that changes how efficiently tides drain away Earth's rotational energy. So, what actually sets the throttle? What controls how fast the moon moves away? And could its escape have raced or stalled in the deep past in ways our simple averages completely miss? The throttle isn't set by the moon at all. It's set by Earth's oceans. Think about pushing someone on a swing. If you hit the rhythm just right, each push adds a lot of energy. If you're offbeat, you barely do anything. Tidal braking works the same way. The moon pulls, the oceans try to slosh, and the question is, how well does Earth respond to that rhythm? Because here's what nobody tells you. The moon's escape speed depends on how easily our oceans can be shaken. Now let's begin with that swing picture and scale it up to planetary size. The tides we see on a beach are just the visible skin of a much bigger oscillation. The real game is how those moving masses of water rub against the seafloor and coastlines, turning organized motion into heat. Deep, broad basins let tides roll more smoothly. Shallow shelves and jagged coastlines make them crash, pile up, and waste more energy. More wasted rotational energy means more angular momentum handed to the moon's orbit, so it spirals outward faster. So the layout of Earth's surface is not just cartography, it's a control knob. Rearrange the continents, change the average ocean depth, redraw the coastlines, and you've changed how strongly tides are raised and how dissipative they are. A world with one big ocean wrapped around the equator will respond to the moon's pull very differently from a world with broken up basins and flooded continental margins. Same gravity, same moon, totally different efficiency. Here's the twist. Some ocean basins can resonate with the tidal forcing period, the roughly 12-hour cycle that the moon drives. When a basin's natural sloshing period lines up with that, the tides are amplified. Like a swing pumped at exactly the right moment, water levels climb higher, currents race faster, and friction with the seafloor skyrockets. That resonance boosts tidal dissipation, and in turn, speeds up the moon's recession. Miss that resonance and the whole system runs much quieter. And yet something is above the planets. Something is below them. In the same way, some eras of Earth's history sit above the present in tidal efficiency, some below, just because the map looked different. In the deep past, supercontinents like Rodinia and Pangaea concentrated land in single clusters, ringed by vast oceans with different depths and shapes. Those ancient geometries almost certainly produced tidal dissipation rates that were higher or lower than today, bending the moon's recession history away from a simple straight line. So when we take the current 3.8 centimeters per year and just run the tape backwards, the numbers don't quite land at the moon's formation age. The math wants a younger moon than the rocks allow. That mismatch is the fingerprint of all those shifting coastlines and drowned shelves we've ignored. It tells us the throttle has been sliding around for billions of years. So how do we actually reconstruct that hidden record of changing tides and drifting days? Pattern interrupt for your brain. The next time you see the moon hanging over the ocean, remember that those waves are literally pushing it away from you. You know the one. That calm postcard picture of a full moon over a silver path on the water. That's not just pretty. That's a transfer of energy and progress. If you want to keep following those long, slow trades that gravity makes across the solar system, we've got a whole playlist waiting for you. Start with the video on how Earth's rotation, The tides and the length of the day have changed since the planet first cooled. Then ride that arc outward into how orbits evolve, how the sun will swell, and how the wider space around us will reshape everything we think is stable. Now let's begin a quieter kind of thinking. When you step outside tonight, the moon will still be there, a little farther than yesterday, on the same locked face in the same familiar orbit, but now, for you, a lot less mysterious. So, instead of wrestling with equations, let's do something more fun. Let's cheat. Let's grab all 4.5 billion years of the Earth-Moon story and slam them into a few minutes of time-lapse in your head. Now let's begin with a scene you almost never picture. A newborn Earth, still glowing, still bleeding magma into space, wrapped in a thick, choking cloud of rock vapor. Out of that chaos, the moon gathers from the debris of a colossal impact. It doesn't politely park where it is now. It hugs in close, only a few Earth diameters away, huge in the sky, fast. You watch this early moon race around a rapidly spinning Earth. A day is just a few hours long. The continents, such as they are, whip through light and dark so quickly you'd get jet lag just standing still. Because here's what nobody tells you. Those monstrous tides you're imagining, climbing hundreds of meters along young coastlines, are not just scenery. They're the engine. In our time lapse, every time the ocean bulges towards the moon and then drags across the seafloor, friction steals a tiny slice of Earth's spin and hands it to the moon's orbit. Gravity is the invisible gear train. Earth slows. The moon climbs. Orbit by orbit, pixel by pixel, the distance grows. So, let's start at the very beginning of the moon's personality. Early on, it spins freely, showing every face to space. But those same tides deform the moon itself, kneading it like hot dough. Internal friction robs its spin of energy until, in your mental movie, the rotation stutters and locks. One hemisphere freezes, forever turned toward Earth. That familiar man in the moon? You know the one. In this fast forward, you watch it slowly swivel into permanent view and then stop. As the moon recedes, the violence dials down. Tides shrink from apocalyptic walls of water to strong, then moderate, then almost cozy. Days stretch, 5 hours, 8, 12, 18. Our time-lapse skims past shallow seas where life starts experimenting with shorelines. Microbes colonize tidal flats. Later, strange early animals time their lives to the rhythm of rising and falling water. Without saying a word, the orbit is writing a schedule, and biology is reading it. Continents drift across the globe like slow-motion ice flows, colliding, tearing apart, raising mountain chains that redirect oceans. Each new configuration reshapes the tides, sometimes cranking the braking effect, sometimes easing it. So the moon's recession speeds up and slows down in our movie, like a long, cosmic heartbeat. Eventually, the frames slow to something that looks familiar. A 24-hour day, a moon the size you recognize, tidally locked, 384,000 kilometers out, still slipping away at 3.8 centimeters per year. Fade up to the present. And yet something is above the planets. Something is below them. Because the Earth-Moon system is still changing in that larger gravitational web. So what does the next chapter of this time-lapse look like if we let it run forward? And forward. And forward. So if the moon is slipping away in that time-lapse, does it just keep going? Does it one day snap out of Earth's grip and start orbiting the sun on its own, like a tiny stolen planet cruising through space? Because here's what nobody tells you. The very process that's pushing the moon away is also quietly setting up the brakes. The tidal torque that's doing all the work doesn't stay constant. It gets weaker, much weaker. As the moon moves outward, Earth's gravity still raises tides, but the difference between the near side and the far side, that gravitational gradient, falls off steeply with distance, so the tidal bulges shrink. The friction in the oceans and crust drops. The invisible handle that Earth uses to fling angular momentum into the moon's orbit starts to slip. You can picture it like a spinning ice skater trying to push a partner on a long rope. The farther away they are, the less leverage you have, until your pushes barely do anything. If we let this play out for absurdly long time scales, something elegant happens. The Earth-Moon system heads toward a tidal equilibrium. That's the state where Earth's rotation period and the Moon's orbital period finally match. 1 Earth day equals 1 lunar month. No lead, no lag, no twisting tidal bulge, no torque. At that point, the conveyor belt of angular momentum shuts down. There's nothing left to transfer. The Moon's recession stalls at a stable distance, still in Earth's orbit around the Sun, not drifting off into some independent solar orbit. It's not escaping. It's just reached the point where gravity and rotation have negotiated a long-term truce. And in that far future picture, the geometry gets wonderfully weird. The Moon is already tidally locked to Earth. You know the one, the same face staring back at you every night. But in equilibrium, Earth would be locked right back. One hemisphere of Earth would always see the Moon hanging in the same patch of sky, frozen over the same landscape, while the other hemisphere would never see it at all. Permanent moon side, permanent moonless side. Days would be as long as months. The Earth-Moon pair would rotate together like two dancers holding a rigid bar, turning once per orbit on a shared plane around the Sun. So, will we ever actually get there? Here's the twist. Probably not. This equilibrium would take far longer than the current age of the universe, while the Sun is on a very different schedule. Long before Earth and Moon can fully lock, the Sun will swell into a red giant, its gravity and radiation rewriting the whole orbital picture. Which raises a much stranger question. What happens to this delicate, slowly freezing dance when the central star itself starts to unravel? So if the Sun is on a countdown, what happens to Earth in the meantime? Our planet doesn't just sit there politely spinning at 24 hours forever. It's dozing off. Very, very slowly. Because here's what nobody tells you. Every time the tides rise and fall, Earth loses a tiny bit of rotational energy. Tidal friction drags on the oceans drag on the continents, and that drag acts like a cosmic brake. The result is simple, but brutal. The rotation slows. The day lengthens. Not by hours in your lifetime, but by milliseconds per century. You can actually see this in the geological record. Ancient corals and tidal rhythmites preserved daily and monthly cycles like a time-stamped notebook. Around 620 million years ago, those layers tell us a day was only about 21.9 hours long, with roughly 400 days in a year. Same orbit around the Sun, different spin. Faster Earth, shorter days, more sunrises packed into one orbit. Today we have an even sharper tool, lasers. We fire pulses at retroreflectors left on the Moon by Apollo astronauts and measure the return time down to millimeters. That's how we know the Moon is receding at about 3.8 centimeters per year, and Earth's rotation is slowing just enough that we occasionally need leap seconds to keep our clocks aligned. Your GPS, your satellites, precise astronomical observations, they all have to account for this creeping change. If you ignore it, your perfect model of the solar system slowly drifts out of focus. Now let's begin to stretch your sense of a day. Push this process forward billions of years, ignoring the sun's tantrum for a moment. The tidal brake keeps grinding. Earth spins more and more slowly as the moon's orbit swells. Imagine a world where a single day is not 24 hours, but hundreds, then thousands. The sun would crawl across the sky, lingering overhead for weeks. Sunrise becomes a season. Sunset becomes another. What does that do to climate? With the same side of the planet facing the sun for such long spans, the day side would bake, the night side would cool toward deep freeze, and the atmosphere would have to work overtime to shuffle heat around. Your winds might organize into gigantic, slow-motion superstorms, circling the planet like a conveyor belt. Ocean currents would reshape. Some regions could swing between blistering heat and brutal cold in a single extended day, challenging anything that wants to live there. So let's start at the very beginning of this future nap. It's the moon's fault. Its gravity raises tides. Those tides rub against the sea floor. And that friction is the hand gently, but relentlessly, pressing on Earth's rotational brake. Our planet is nodding off while the moon drifts away, stretched out along an orbital plane that looks flat in the textbook picture, but hides this deep exchange of energy. And yet, something is above the planets. Something is below them. In the next part, we're going to zoom out and ask how this slow-motion yawn of Earth fits into the larger gravitational web, tying the whole Earth-Moon-Sun system together. But there's another consequence of this slow-motion yawn that feels a lot more personal. You don't need equations to feel it. You just have to remember the last time you saw the sun disappear in the middle of the day. We live in an age of total solar eclipses. That sentence sounds normal until you realize it hasn't always been true, and it won't be true for very long. Because here's what nobody tells you. Totality is a cosmic coincidence on a deadline. Right now, the moon is about 400 times smaller than the sun, and about 400 times closer. Those two numbers line up so precisely that, from the ground, the moon and the sun appear almost exactly the same size in the sky. You know the one. That perfect black coin that just barely covers the solar disk, letting the corona flare out like ghostly white fire. That one-to-one match is the only reason total eclipses exist at all. But the moon is sneaking away, centimeter by centimeter, every year. As its orbit grows, its apparent size shrinks. The circle it draws against the sky tightens. Fast forward a few 100 million years, and that black coin won't be big enough to cover the sun completely. The geometry still lines up. The planes of the orbits still intersect. But the moon's shadow will never quite erase the star behind it. Instead, future observers, if there are any, will only see annular eclipses, the so-called ring of fire. The moon will slide in front of the sun and leave a blazing halo all the way around its edge. Beautiful? Absolutely. But never night in the middle of day beautiful. Never planets popping out, temperature dropping, animals confused, you feeling the hair rise on your arms because noon just turned to twilight. So, let's start at the very beginning of that future. Run the orbital models forward, and you find that in a few 100 million years, totality ends. Past that point, from any point on Earth's surface, the moon's apparent diameter will always be smaller than the sun's. Total eclipses will be physically impossible. The last one will happen. The shadow will sweep across the planet. And then that chapter just closes. Which means our era is special in a way textbooks almost never say out loud. We live in a narrow window when the Earth-Moon distance is just right, When gravity and orbital history line up to let you stand in exactly the right place and watch the universe do a magic trick, it will eventually retire. And yet, something is above the planets. Something is below them. Because once you realize that even eclipses are temporary, the whole Earth-Moon configuration stops feeling timeless and starts feeling like what it really is. One fleeting configuration in a much longer story. In the next part, we'll pull the camera back again and ask how this fading eclipse era fits into the wider evolution of the solar system's orbits and the sun that's driving them all. So if eclipses are already fading, let's push the thought experiment all the way. What if the moon had started out much farther away? What kind of Earth would you actually be standing on right now? Now let's begin with the most obvious ripple effect: tides. A more distant moon means weaker lunar gravity, pulling on our oceans, which means smaller tidal ranges. High tide wouldn't climb as high up the beach. Low tide wouldn't drain the shoreline as dramatically. The violent surf zones and broad, exposed mudflats, the one from nature documentaries, would shrink into gentler, narrower coastal strips. Because here's what nobody tells you. Those in-between areas, the intertidal zones that get soaked, then dried, then soaked again, are biological pressure cookers. Today they're full of barnacles, crabs, seaweeds, and microbial films that survive being alternately drowned and baked. If the moon had always been far away, those zones would be thinner, calmer, and less extreme. Different game, different training ground. There's a long-running hypothesis that strong, regular tides helped life crawl out of the ocean. Picture an early Earth with the moon much closer, raising tides that surged far inland, then retreated, leaving behind warm, salty pools. Those pools would concentrate organic molecules, then periodically dry, forcing early organisms to handle both water and air. Did that tidal rhythm act like a planetary boot camp for lungs, limbs, and waterproof skin? Or would evolution have found another path entirely without those dramatic wet-dry cycles? With a distant moon, you still get tides from the sun, but they're smoother, less extreme. The daily pulse that sloshes entire coastlines back and forth would be muted. That doesn't just change beaches, it reaches deep into the oceans. Tidal mixing today helps stir nutrients from the deep back toward the surface, where sunlight can power photosynthesis. Turn that down and you alter how efficiently the ocean recycles its raw materials. So now imagine a world where the great ocean conveyor belts run a little differently, where plankton blooms are weaker or shifted, where entire food webs grow up on a different energy budget. Fewer nutrients reaching the surface could mean fewer fish, fewer seabirds, different climate feedbacks. And yet something is above the planets. Something is below them. The same gravity that sculpts orbits is quietly sculpting ecosystems. We can't run a controlled experiment with two Earths, one with a close moon and one with a distant one. But it's completely reasonable to think that changing the Earth-Moon distance would nudge evolution onto a different track. Maybe intelligence still appears, but in the oceans. Maybe complex land life arrives later, or looks nothing like us. Which leads to the unsettling question: if the moon had always been small in the sky, hanging far out in its orbit, would there ever have been creatures with hands, telescopes, and questions, staring up and wondering why it was so far away in the first place? Hold that thought, because to answer it, we have to zoom out to the entire solar system and ask how many other worlds get this kind of gravitational partner at all. So before we race off to other worlds and other orbits, we have to close a loop we opened earlier. Remember that challenge near the start, when we asked you to guess how long a day was back when dinosaurs were stomping around under a brighter, closer moon? Let's cash that in. Because here's what nobody tells you. Your dinosaur-era day was not some wild alien number. During the late Cretaceous, geological evidence suggests days were about 23.5 hours long, not 10, not 40, just a little shorter than today. The year still took the same amount of time to orbit the sun, but you could have squeezed in roughly 372 of those shorter days instead of our 365. That number doesn't come from a guess. It comes from the rock record quietly keeping time. Ancient corals and tidal rhythmites preserve daily and monthly cycles like tree rings. And when geologists count those bands in Cretaceous layers, they see more days per year than we have now. More spins of Earth for the same trip around the sun means each spin had to be shorter. Now let's rewind even further. About 620 million years ago, long before dinosaurs, those same kind of records show days that were only about 21.9 hours long, with around 400 days packed into a year. So on our timeline, we've gone from 21.9-hour days to 23.5-hour dinosaur days to the 24-hour days you set your alarm by. Same planet, same moon, completely different rhythm. Here's the pattern interrupt. When we talk about the moon fleeing into space, it sounds dramatic, like it should rip our calendar apart. But from the point of view of a single creature, it's almost invisible. A T-Rex living its best, slightly terrifying life would not notice that its day was 23.5 hours instead of 24. You wouldn't either. You just show up to work a little earlier in cosmic terms. And yet, over hundreds of millions of years, that tiny change in day length adds up to a completely different picture of Earth's spin and the moon's orbit. The moon steals a bit of rotational energy, slides a little farther out, and Earth pays the bill with longer days. So, let's start at the very beginning. Even the thing you think of as fixed, the length of a day, is really part of a slow, ongoing negotiation between gravity, oceans, and a companion world. You know the one. The moon that looks so steady in your sky is quietly editing your clock, 1 millisecond at a time. In a moment, we're going to zoom back out to the whole solar system and ask, how many other worlds have their days rewritten by a nearby moon? And how many are spinning free, with no one to trade angular momentum with at all? But here's the twist. The moon isn't just stretching our oceans and stealing milliseconds from our day. It's also quietly holding our entire planet steady, like a cosmic hand on a wobbling top. Now let's begin with something you probably learned in school and then never really questioned. Earth doesn't spin straight up and down. Its axis is tilted about 23.5 degrees relative to its orbit around the sun. That tilt is why you get seasons, why summers lean toward the sun and winters lean away. Without it, the solar system would feel flatter, the year more monotonous, like a planet stuck in permanent late March. But a tilted axis is not nailed in place. In principle, it can wobble, slowly, relentlessly. Because here's what nobody tells you. In the long game, gravity from the sun, from the other planets, even from the distant mass of the Milky Way, is always trying to torque that spinning Earth, nudging the tilt one way, then another. Left on its own, our axis would be far more chaotic. You can see the extreme version of this if you look around the solar system. Mars, for example, doesn't have a big moon to lean on. Its tilt can swing by tens of degrees over time, taking it from something like Earth-style seasons to wild scenarios where the poles point almost sideways into space. Imagine ice caps melting, then refreezing at new latitudes, climate belts marching north and south like they've lost the script. Earth avoided that fate because it has a heavyweight partner. The moon's gravity pulls on our equatorial bulge and acts like a stabilizing anchor, damping down the worst of those tilting impulses. The axis still precesses and drifts a little, but instead of careening between 0 and 60 degrees, it oscillates within a relatively narrow band. That's a big deal for climate. It means coastlines, forests, and ice sheets don't have to reinvent themselves every few million years. Simulations where you delete the moon from the equations are brutal. Run Earth forward in time without its satellite, and the tilt can wander chaotically, jumping from modest angles to extreme ones that would turn the planet into a climate roller coaster. Continents that were temperate could spend geologic ages under permanent polar night. Others would bake under a sun that barely sets. And here's where our recession story comes back in. A closer moon in the past meant a stronger stabilizing grip. When it orbited just tens of thousands of kilometers away, its ability to hold Earth's tilt in line was even more pronounced than it is today. As it has retreated to its current distance, that stabilizing torque has been very slowly weakening. So as the moon keeps slipping outward, centimeter by centimeter, what happens to that delicate balance? Over tens or hundreds of millions of years, does Earth's axial tilt start to wander a little more, making long-term climate cycles sharper, deeper, stranger than the ones we know? In a moment, we're going to zoom out and ask how unique this arrangement really is in the broader picture of planetary systems. So if our moon is quietly sneaking outward, the obvious question is that normal, or are we the weird ones? Because here's what nobody tells you. Tidal forces are running the same energy trade all over the solar system, and not every moon is making a graceful exit. Now let's begin with a world that flips your intuition. Mars, 2 tiny moons, Phobos and Deimos, barely more than a captured rubble. You know the one that shows up in sci-fi as a lumpy rock hanging over a red horizon? That's Phobos. And unlike our moon, it isn't drifting away. It's spiraling in. Here's the trick. With Earth, the moon orbits slower than Earth spins, so gravity pulls the tidal bulge slightly ahead of the moon and slings it outward. Around Mars, Phobos orbits faster than Mars rotates, so the tidal bulge lags behind, and gravity acts like a brake on the moon's orbit instead of a boost. Its orbit shrinks. Bit by bit, Phobos is losing altitude, doomed to either crash into Mars or be torn into a ring in tens of millions of years. Same physics, opposite outcome. So, let's start at the very beginning of the rule. Compare a planet's rotation period to a moon's orbital period. If the planet spins faster than the moon orbits, the moon can be pushed outward, the way our moon is. If the moon whips around faster than the planet turns, gravity drags it inward. Outward migration, inward death spiral. One simple ratio decides which picture you get, and yet something is above the planets. Something is below them, not in the flat geometric sense this time, but in terms of energy. Some moons, like ours, are climbing the energy hill. Others, like Phobos, are sliding down it. Now zoom out to the giant of the solar system, Jupiter. Here, tidal forces don't just move moons, they cook them. Take Io, locked in a tight orbit, constantly tugged by Jupiter and nudged by neighboring moons. Io is being flexed like a rubber ball in a hydraulic press. That flexing turns orbital energy into heat. Result: the most volcanically active body we know, with lava fountains blasting higher than Mount Everest is tall. Tides there don't just raise oceans, they melt rock. In some Jovian moons, that same tidal flexing keeps subsurface oceans liquid, driving chemistry that might one day hint at life. Our tides give us gentle coastlines and slowly longer days. Out there, tides build volcano worlds and hidden seas. Because once you see Mars's doomed Phobos and Jupiter's tortured Io next to our slowly escaping moon, you realize tidal evolution is a universal process, not a local quirk. So what happens if we pull back even farther to planetary systems we can't see in this kind of detail yet and ask, out there, which moons are escaping, which are falling, and which are being torn apart right now? So here's the twist that makes the moon's escapes suddenly click into place. This isn't just a story about distance, or orbits, or some abstract gravitational dance. It's a story about energy, where it starts, where it goes, and how it gets lost along the way. Because here's what nobody tells you. The moon drifting away is really Earth's spin bleeding out. When Earth was younger, it rotated faster. That fast, ordered spin is a huge reservoir of rotational energy. Tides, raised by the moon's gravity, reach out and grab that spin like invisible brakes smeared around the planet. The friction between those moving tidal bulges and the sea floor doesn't just slow Earth down as an afterthought. That friction is the mechanism that moves energy around the system. No process is perfectly efficient. So as the oceans slosh back and forth, the neat, coordinated rotation of Earth gets partially converted into messy, microscopic motions in water molecules and rock. That motion gets randomized and ends up as heat. You don't feel the planet warming under your feet each time a wave hits the shore, but it's there, hiding in the bookkeeping of thermodynamics. So, let's start at the very beginning of this trade. Earth spins. The moon raises tides. Because the tidal bulge is pulled a little ahead of the line connecting Earth and moon, gravity between that bulge and the moon does something sneaky. It drags the moon forward in its orbit. A forward tug in orbit means more orbital energy. More orbital energy means a higher orbit. The moon climbs, centimeter by centimeter, into a wider path through space. But that free upgrade isn't free at all. It's bought with Earth's rotational energy and a surcharge paid as heat in the oceans and crust. The moon's higher orbit is like a savings account of mechanical energy, slowly filled over billions of years, while Earth's spin is the checking account being drained. You get a longer day on Earth, a larger orbit for the moon, and a universe that's just a tiny bit warmer in the smallest possible way. And this is pure thermodynamics. Over time, ordered motion tends to decay into disordered motion. A clean, fast spin is very ordered. Random jiggling of atoms as heat is very disordered. The second law of thermodynamics says the total entropy of an isolated system tends to increase, and the Earth-Moon pair is doing its part, turning organized rotational energy into a less organized mix of orbital motion plus heat. Now let's begin to see the Earth-Moon system differently, not as two static balls in a flat textbook picture, but as partners in a slow, relentless redistribution of energy. One world's spin becomes another world's orbit, with friction quietly cashing out the difference. And yet, something is above the planets. Something is below them. So what happens when we zoom out and ask how this same energy logic plays out in entire planetary systems across the galaxy? So before we zoom all the way out to planetary systems, we have to clean up something closer to home. Because here's what nobody tells you. A lot of what you've casually picked up about the moon escaping is just wrong. Not evil textbook wrong. Quietly misleading wrong. The first myth sounds intuitive. The moon is being blown away by the sun. Solar radiation, solar wind, some invisible pressure pushing it off into space like a cosmic beach ball. It feels right, because we've seen diagrams where sunlight streams past Earth and the moon's like a river. But that picture misses the real engine. The force that matters here isn't a breeze in space. It's gravity stretching Earth into a slightly squashed shape and dragging our oceans around. Those shifting tidal bulges pull on the moon, the seafloor pulls back on the water, and friction turns Earth's spin into heat while handing angular momentum to the moon's orbit. So, let's start at the very beginning of the second myth, that the moon just glides around us in a perfect, unchanging circle. You know the one, the flat white ring in a clean textbook diagram. In reality, the moon's orbit is slightly eccentric, more like a squashed oval, and it wobbles. Its distance swings by tens of thousands of kilometers each month, and over longer time scales, that oval slowly evolves as tides reshape the system. The 3.8 centimeters per year we measure with lunar laser ranging is an average, not a fixed cosmic law. Then there's the dramatic version. The moon is about to fly away and leave Earth behind. Is it escaping our gravity? Not even close. Right now, the moon is deeply bound. To actually leave, it would need far more energy than tides can ever deliver. What tides are doing is nudging the system toward an eventual tidal lock equilibrium, where one day, a month equals one day on Earth, and both worlds always show the same face. If nothing else in the solar system interfered and the sun didn't evolve, that would take far longer than the current age of the universe. So no, you don't have to schedule a farewell party. Another tempting myth, that this slow recession is behind every short-term disaster. Big earthquake, sudden climate shift, it must be the moon drifting away. But the recession is glacially slow. Over your entire lifetime, the moon moves outward by less than the width of a small city. That's not the kind of change that snaps faults or flips climate by itself. Local plate tectonics, ocean atmosphere dynamics, and solar input dominate those fast events. Now, let's begin to tie all of this together. Each myth is really the same mistake, swapping a deep, friction-driven exchange of angular momentum for a quick, dramatic push. Once you see the moon's motion as a long negotiation between tides, gravity, and time, you're ready to ask a bigger question. How far back can we rewind this dance? And what did the Earth-Moon system look like when it first began? So let's start at the very beginning of that dance and then cheat. We've been rewinding the real Earth-Moon story, but what if we changed the opening move? What if the moon had started out much farther away than it actually did? On our Earth, the newborn moon orbited close in, so tides were enormous, and tidal friction was brutal. The ocean sloshed hard against the sea floor, dragging on Earth's rotation, turning spin into heat and slowly boosting the moon's orbit. Because here's what nobody tells you. That early violence is why our days stretched from a frantic few hours to the 24-hour rhythm you live inside right now. So imagine a different picture. Same planet. Same moon. But the moon begins life already tens of thousands of kilometers farther out. Instantly, everything changes. Weaker gravity from a more distant moon would raise smaller tides, so the tidal bulges would be lower and the friction gentler. Earth would still lose rotational energy, but more slowly. That means that in this alternate timeline, your clock would not say 24 hours. Days could still be closer to 20 hours, or even less, because the planet just hasn't been braked as hard for the last 4.5 billion years. Nights would feel shorter, winds and weather patterns would be tuned to a faster spin, and the coasts, they would be different worlds. With weaker tides, the rise and fall of the ocean would be more modest, more like a gentle breathing than a twice-daily lunge inland. Those broad tidal flats that expose and flood over and over are thought to have been chemical playgrounds for early life, and later, stepping stone habitats for creatures crawling from sea to land. If the tidal range had been smaller, would evolution have taken the same routes? Would complex life have arrived later, or through totally different coastal ecosystems? You know the one, the nature documentary shot at low tide, where everything is barely hanging on. In our alternate Earth, that entire scene might not exist. There's another twist. A closer moon helps pin Earth's axial tilt in place, like a stabilizing hand on a spinning top. A more distant moon exerts a weaker torque, so the planet's tilt could wander more over millions of years. That means ice ages that swing harder, tropical belts that drift farther, climate zones that yo-yo in and out of habitability. Could a civilization like ours ride out those wild cycles? Or would the solar system feel like a less friendly neighborhood from the surface of this restless world? We can't run that alternate universe in a lab, so we can't say exactly how different things would be. But the implication is clear. Change the starting Earth-Moon distance, and you rewrite coastlines, climates, and clocks. And yet, something is above the planets. Something is below them. To really see how sensitive our story is, we now have to push the moon the other way and ask, what if it had started out even closer than we think? So let's answer that question we just posed and drag the moon inward in your imagination, only to slam it back into reality. Because here's what nobody tells you when they talk about oceans boiling and days shrinking and coastlines rewriting themselves. In your lifetime, the moon barely budges. Right now, the moon is slipping away at about 3.8 centimeters a year. That's roughly the width of your finger. Not per day, per year. If you live a long life, say 80 years, the grand total of this dramatic escape is just over 3 meters, the distance from one end of a small room to the other. For all the talk of billions of years and wild tidal forces, the version of the sky you grow up with is basically the version you die with. You will never walk outside, look up and think, the moon looks smaller than when I was a kid. It won't happen. Your eyes aren't nearly that precise. Your brain is even worse, constantly auto-correcting for brightness, clouds, the moon's position on the horizon, and that whole moon illusion where it looks huge near the skyline and tiny overhead. On human timescales, the orbit is changing, but the picture in your head is frozen. So how do we know it's moving at all? This is where the story stops feeling like mythology and starts feeling like an experiment. During Apollo, astronauts left retroreflectors on the lunar surface. We fired lasers at them from Earth. Wait about 2.5 seconds for the light to go there and back, and time that journey so precisely we can see the moon drift away millimeter by millimeter. The most romantic long-distance relationship in the solar system is being monitored with boring lab equipment. Pattern interrupt. You've never seen the moon move away. You've only seen graphs. And yet those graphs are so consistent that when we combine them with theory and with ancient clues, like fossil corals and tidal rhythmites that record shorter days hundreds of millions of years ago, we get a single, coherent story of a world where gravity is quietly rearranging the clock. Now let's begin to zoom out from the moon itself and ask what this really means. Most of cosmic evolution is like this: glacial, invisible. On the scale of a news cycle or human life, the universe looks static. The solar system feels flat and fixed. The moon's orbit feels permanent. The constellations feel eternal. But beneath that calm picture, orbits are stretching, stars are drifting, galaxies are colliding in slow motion you'll never witness directly. So if we needed lasers on the moon, fossils and rocks, and careful theory just to notice a few meters of change over a lifetime, what else is shifting just beyond our senses? And what does that say about our ability to catch other slow motion changes unfolding across the universe right now? So if we needed fossils and lasers to catch the moon sneaking away, how do we catch Earth itself slowing down? You can't exactly look at a spinning planet and see it dragging its feet. The change is too tiny, too slow, but it does leave fingerprints in the one thing you check every single day: time. Now let's begin with a clock that doesn't care about sunrise or sunset at all. Atomic clocks. These are the most precise timekeepers we've ever built. They define the second, not by Earth's rotation, but by the vibration of atoms, usually cesium, flipping between energy states with mind-numbing regularity. You could say they're like tiny tuning forks made of matter itself, ringing billions of times per second. And unlike our planet, they don't get tired. Because here's what nobody tells you. For most of human history, time literally meant how long it takes Earth to spin once. Sundials, mechanical clocks, even old observatories all assumed the planet was the metronome. When that was your reference, you never noticed the problem. The metronome and the music were drifting together. But once we started comparing atomic time to astronomical time, the illusion cracked. Astronomical time is tied to Earth's rotation and orbit around the sun, the old celestial rhythm we used to trust. Atomic time is this cold, unblinking yardstick. Put them side by side, and they don't quite agree. At first, the difference is microscopic, fractions of a second. Then, over years and decades, those fractions add up. You get a slow, creeping mismatch between what the atoms say and what the sky is doing. So what do we do when our planet refuses to keep up with our clocks? We cheat. Every so often, timekeepers around the world add a leap second to coordinated universal time. One extra tick at the end of June or December, so your phone, your GPS, and the official timescale don't drift away from Earth's slightly slowing spin. It's like quietly slipping an extra frame into the movie so the projector stays synced with the reel. And yet something is above the planets. Something is below them. In this case, it's tidal friction, tugging on oceans, dragging on the seafloor, bleeding rotational energy into heat and into the moon's orbit. The same process that's pushing the moon higher in its path is also forcing us to patch our clocks, to rewrite our calendars in tiny increments you never notice. This is the unnerving part. A cosmic scale interaction between two worlds is literally encoded in the software that runs your navigation system. Your sense of now is being adjusted because gravity is moving the moon. So what else in your everyday life is quietly being edited by distant motions you never see? So if the moon can quietly reach into your phone and edit your sense of time, what is it doing to something even more fragile? Your coastlines, your oceans, the living skin of water wrapped around this planet. Because here's what nobody tells you. As the moon keeps receding, the tides that feel so eternal to you are slowly being turned down. Not this year, not in your lifetime, but over millions of years, that gravitational tug-of-war weakens, and the shape of the shore begins to answer to a different script. Right now, tides are like a planetary sanding machine. They drag water back and forth across beaches, bays, and cliffs, chewing rock into sand, flooding estuaries, carving deltas. In a stronger tide past, that sanding machine was even more aggressive. In a weaker tide future, the daily reach of the sea shrinks. Storm waves and rising or falling sea levels will still remodel the coasts. But the regular, twice-a-day sculpting gets softer, more localized, less able to haul sediments long distances. Over geologic time, that means some tidal flats will harden into more stable shorelines, while other places that owe their very existence to big tidal ranges will fade out of the picture. Take the Bay of Fundy, you know the one, famous for tides that can rise higher than a 4-story building. Those extremes only exist because the bay's shape and depth line up just right with the period of the moon-driven tides, like a child pumping a swing in perfect rhythm. As the moon creeps outward and the length of Earth's day stretches, that rhythm drifts. The resonance detunes. Over tens of millions of years, Fundy's legendary tides will calm. The vertical walls of water will flatten, and its mudflats and cliffs will evolve under a quieter beat. Now let's begin to think beyond the shoreline. Tides don't just move water side to side. They knead the oceans from top to bottom. That vertical mixing helps drag oxygen from the surface into the deep sea and hoist nutrients back up where sunlight can drive photosynthesis. Weaker tides mean weaker mixing. In some basins, deep waters could become more sluggish, less ventilated, forcing marine life to adapt to thinner oxygen and different nutrient delivery routes. But tides are only one player. Global circulation is also powered by winds, by temperature and salinity gradients, by Earth's rotation twisting currents into great spirals. Even as the lunar pull fades, storms will still whip the surface. Polar waters will still sink, and the planet's spin will still organize flows into gyres and boundary currents. The system won't switch off. It will retune. And yet, something is above the planets. Something is below them. On cosmic scales, even your oceans are part of that layered dance. Gravity, rotation, orbit, all trading energy so slowly you mistake it for stillness. The same process that is lengthening our days is, tide by tide, rewriting a future coastline no human will ever see. But if the moon can redraw the map of Earth's oceans, what will it do to the moon itself? To answer that, we have to do something strange. We have to listen to rocks, not just any rocks. Thin, delicate bands of ancient mud, stacked like pages in a diary, each one written by the pull of the moon. Because here's what nobody tells you. The moon has been leaving a paper trail on the seafloor for billions of years, and in a few lucky places, that trail has been frozen in stone. Geologists call these records tidal rhythmites. Picture a shallow coastal plain, flooded and drained twice a day as Earth spins under the moon. Every high tide brings in a pulse of sediment. Every low tide lets the water fall away, leaving a thin layer behind. Over days, months, and years, those layers stack up. Thin, thick, like a heartbeat recorded in mud. Now let's begin to read that heartbeat. Not all tides are equal. When the sun, earth, and moon line up, their gravity pulls in the same direction, and the tides grow larger. Spring tides. A week later, when the sun and moon are at right angles, their pulls partially cancel and the tides shrink. Neap tides. In a rhythmite's outcrop, that cycle shows up as a repeating pattern of thicker and thinner bands, waxing and waning every 2 weeks or so. So, let's start at the very beginning of the detective work. If you count how many daily tidal layers fit between one spring tide maximum and the next, you're literally counting how many days fit into half a lunar month at that time. Double it, and you get the length of the lunar month. Count how many such cycles fit into a full year's worth of seasonal changes, and suddenly, the rock is telling you how many days there were in a year. You know the one. The same year defined by Earth's orbit around the sun, but sliced into many more, much shorter days. Here's the pattern interrupt. Those rocks don't say 365. They say closer to 400. In formations like the 620 million-year-old Elatina Formation in Australia and the Big Cottonwood Formation in Utah, tidal rhythmites show that there were about 400 daily layers per year, and each day lasted only around 21.9 hours. Earth was spinning faster. The moon was closer. The whole Earth-Moon system was tidal wound, exchanging energy through tides more intensely than it does now. And yet, something is above the planets. Something is below them. Even here, in these flat slabs of sandstone and shale, you're seeing a vertical dimension in time. The moon's orbit slowly expanding. Earth's rotation slowly breaking, all encoded as millimeter-scale stripes. This is what makes it feel like detective work. You stand in front of an ancient cliff, count tiny bands with a hand lens, and from that, reconstruct the moon's recession history and the length of an ancient day. Once you realize rocks can do that, you start to wonder, if we can read the past this way, how far into the moon's future can we project? So if rocks can rewind the story, what happens when we fast forward it? Push the equations not just millions of years ahead, but billions, tens of billions, until the moon's slow motion escape finally stops. Because here's what nobody tells you. The moon isn't going to drift away forever. If nothing else in the solar system interfered, if the sun just kept shining politely in the background, gravity and friction would keep working the problem until Earth and Moon reach a kind of truce. A final configuration, a locked stare. Now, let's begin with the end state. Imagine a far future Earth where a day is no longer 24 hours, but something like a month long. Earth's spin has been drained, bled off by tides, until it matches the moon's orbital period. One full rotation of Earth equals one full orbit of the moon. The same rhythm, perfectly synced, like two dancers finally moving in step after an absurdly long rehearsal. In that world, one hemisphere of Earth always faces the moon. Always. If you live there, you grow up with the moon, nailed to one spot in the sky, never rising, never setting, just swelling and shrinking as its sunlit half turns toward you and away. You know the one, that familiar face with the dark Maria making a lopsided pattern. It would hang over your oceans and continents like a permanent lantern. On the far side of Earth, though, the moon is pure legend. Entire civilizations could rise and fall without anyone ever seeing it with their own eyes. No crescents, no eclipses, no full moon hikes. Just stories from the other side of the world about a cold white disk that never moves. And the tides? That's the strangest part. With Earth and Moon tidally locked, there's no regular daily rise and fall driven by the moon sweeping overhead, because from your location the moon doesn't sweep at all. The big tidal bulges line up with the moon and just stay there. You'd still get slower, more subtle variations from the sun's gravity, from the slight wobble in the orbit, from continents shifting over geologic time. But the familiar twice-a-day rhythm would be gone. Surfers in that era would have a very boring time. There's a catch, of course. This takes time. Not just longer than humanity time. We're talking tens to hundreds of billions of years of tidal braking to get there. That's far beyond the sun's entire stable lifetime. Long after the sun has swollen into a red giant, shed its outer layers into a glowing cloud, and cooled into a white dwarf, the Earth-Moon system would still be grinding towards that lock. So this perfect mutual stare, it's a theoretical endgame, not a scheduled event. And yet something is above the planets. Something is below them. On these scales, our current arrangement, spinning rapidly, moon still retreating, is just a brief dynamic phase in a very long orbital negotiation. The real question is, what interrupts the process first? The sun's death, or some passing gravitational intruder we haven't even met yet? So if the Earth-Moon tidal endgame is a negotiation, we have to ask a brutal question. Who owns the building the meeting is happening in? Because the quiet landlord in this story is the sun, and it has its own schedule. Now let's begin with the part that sounds like science fiction, but is just standard stellar evolution. In about 5 billion years, the sun will run out of hydrogen in its core. When that nuclear fuel is gone, gravity wins for a while, the core contracts, the outer layers respond by swelling, and our calm yellow star balloons into a red giant. The whole inner solar system stops being a gentle, stable backdrop and turns into a very different neighborhood. But you don't have to wait 5 billion years in this mental picture for things to get ugly. Long before the sun becomes a red giant, its luminosity slowly creeps upward. Because here's what nobody tells you. The sun is already brightening over time. Give it a few 100 million to 1 billion years, and that extra energy starts to matter. More sunlight means more heating. More heating means feedbacks that push Earth out of the comfortable zone. Run that forward, and you get a planet that bakes. Oceans that once powered tides and weather begin to boil away. Water vapor, a powerful greenhouse gas, thickens the atmosphere, trapping even more heat. Eventually, the oceans are gone, the surface is scorched, and the atmosphere itself can be stripped by intense radiation and the solar wind. Tides still exist in principle, but the blue world that made them so dramatic is a very different, darker picture. At the same time, the sun is losing mass. Even today, it sheds material through the solar wind and radiation. During the red giant phase, that mass loss accelerates, blowing a vast cloud of gas and dust into space. Less solar mass means weaker gravity. Weaker gravity means Earth's orbit can expand, drifting outward to conserve angular momentum. The moon, still bound to Earth, feels this changing gravitational environment as the whole system moves through a shallower part of the sun's gravity well. All of this chaos is terrible for slow, delicate processes. The gentle transfer of rotational energy that's been pushing the moon outward for billions of years relies on long, stable conditions. When the sun swells, brightens, and sheds mass, it doesn't politely wait for Earth and Moon to finish, tidally locking. It barges in, changes the orbits, bakes the oceans, and quite possibly ends the negotiation early. So the moon's recession is powerful, yes, but it doesn't operate in isolation. It's nested inside the life cycle of the sun itself. The real twist is this. Before Earth and Moon can settle into that final synchronized dance, the ballroom may literally evaporate. The question is, what happens to their partnership as the ceiling catches fire? So if the ballroom is catching fire, we need a different way to watch the dance. Not a snapshot, a timeline. Because here's what nobody tells you. That classic picture of the moon as a neat circle around Earth, it's lying to you by being too flat. Don't imagine a coin orbiting a marble. Imagine a stretched spring drifting through space. Each loop of the spring is one orbit of the moon, but as time flows forward, the whole Earth-Moon system is gliding along the sun's path, and the sun is orbiting the galaxy. The result isn't a circle on a page. It's a spiral carved into space-time itself. You know the one. The diagram orbits, all sitting still. Now tilt it, pull it, let it move. Now let's begin to zoom out in a different direction. Not left or right, not up or down, but into a weird abstract space where each point isn't a place. It's a state. Picture a three-dimensional graph where the axes are length of Earth's day, distance to the moon, and tidal strength. In that invisible space, Earth and moon are just one moving point, tracing a slow curling curve. At the far end of that curve, near the beginning, Earth is spinning fast. A day is only 5 hours long. The moon hangs close, maybe just a few Earth diameters away, huge in the sky, tides towering and violent. Gravity is the same, but the way it's rearranging oceans and crust is on hard mode. That's one waypoint on the curve. Slide forward, and the point moves. Tidal friction keeps bleeding rotational energy, handing it to the moon's orbit. The spiral stretches. Now we hit a spot we can actually check. Around 620 million years ago, fossil corals and tidal rhythmites tell us days were about 22 hours long, with roughly 400 days in a year. Same year, different calendar. The moon is farther out, the tide's a bit calmer, the curve bending but not broken. Keep following the path and we arrive at us. 24-hour days, about 365 days in a year. The moon parked at roughly 384,000 kilometers, receding at 3.8 centimeters per year. This is just one tiny bead on the long necklace of states the system passes through. And yet, something is above the planets. Something is below them. In this abstract space, our normal is just a thin slice. So where are you on that curve? You're sitting in the brief epoch where the moon is the right size and distance to make perfect total solar eclipses, where days feel stable enough to build civilizations around clocks. That's not a permanent feature of the solar system. It's a coincidence of timing. Seen in 4 dimensions, the moon's slow escape stops being a trivia fact and starts reading like a chapter in a cosmic biography. The plot isn't over. The question is, what kind of scene comes next on that curve? So let's pull that whole curve together and give you a new picture to carry around in your head. Not a postcard of a frozen moon politely circling Earth. A journey, a slow-motion escape scene that's been running since before there were continents, let alone calendars. So, let's start at the very beginning. A young Earth gets sideswiped by a Mars-sized body. Vapor and rock explode into space, and a glowing ring of debris condenses into a moon that orbits absurdly close in. The sky is dominated by this huge molten sphere. Tides are brutal. Days whip past in a few hours, and the whole system is spinning like a freshly formed solar system miniature. From that chaos, one simple rule emerges: conserve angular momentum and let gravity do the bookkeeping. Because here's what nobody tells you. The moon's escape isn't a push from some mysterious force. It's a trade. Earth starts out spinning fast, raising tidal bulges in its oceans. But Earth rotates quicker than the moon orbits, so those bulges don't point straight at the moon. They're dragged a little ahead, like a wave racing in front of a boat. Those lopsided bulges pull on the moon with their gravity. The moon pulls back. That tug of war does 2 things at once. It steals rotational energy from Earth and hands it to the moon's orbit. Inside the oceans, friction grinds that law spin into heat. In space, the payout shows up as the moon climbing to a slightly higher orbit every year. Tiny step, enormous time scale. Same basic physics as a skater slowing their spin by flinging a weight outward, just stretched across a planet-moon system instead of an ice rink. How do we know this isn't just a neat story? Because the rocks keep receipts. Ancient tidal rhythmites and fossil corals show more than 400 daily layers per year, meaning days were shorter and years had more sunsets packed in. Atomic clocks today catch Earth's rotation drifting by milliseconds, while lasers bounced off Apollo reflectors track the moon, slipping away at about 3.8 centimeters per year. That's not a theory, that's a measured getaway. Put those clues together and the consequences stop feeling abstract. Your 24-hour day is a moving target, slowly stretching as Earth's spin leaks into the moon's orbit. Tides are very gradually weakening. Total solar eclipses are on a timer. One distant day, the moon's apparent size will be too small to cover the sun completely. And far, far beyond the sun's comfortable lifetime, the math points toward a final configuration. Earth and moon tidally locked, each showing one face to the other, turning together like a double world in a long, shared twilight. So when you look up now, don't see a perfect circular orbit drawn on a flat plane. See an ongoing exchange of energy and motion, a quiet conversation between rotation and revolution. The question is, what happens when other players in the solar system start whispering into that conversation too? That quiet conversation between Earth and Moon doesn't just shape orbits. It rewrites what you think normal even means. Because here's what nobody tells you. The things you use as anchors in time and in the sky, the length of a day, the size of the moon, the rhythm of the tides, are not permanent settings. They're temporary arrangements in a universe that refuses to sit still. 400 million years ago, there were about 400 days in a year. A day was barely 22 hours long. Same planet, same sun, completely different clock. You know the one. The mental picture where the moon has always been right there. Same distance, same face, rising over the same kind of ocean, while the same 24-hour day ticks by. It feels comforting. Our brains crave cycles that come back exactly, calendars that repeat, a sky that behaves. But the tides don't care what feels stable to you. Every wave dragging across the sea floor is ever so slightly renegotiating your calendar. So, let's start at the very beginning of this intuition problem. We grow up with clocks on the wall and months on a page, and they seem absolute. A second is a second. A day is a day. Full stop. Then you learn that Earth's rotation is slowing because of tidal friction, that energy is leaking from spin into the moon's orbit. And suddenly, even your wristwatch is participating in a slow-motion gravitational drama. The constant you trusted is actually a moving target, and yet something is above the planets. Something is below them, not in the sense of a literal up or down, but in the sense of time scales that tower over human life. Your senses are tuned for heartbeats and weather patterns, not for million-year tides. Without scientific tools, the moon's recession is invisible. With laser ranging, fossils, and physics, we can measure a retreat of 3.8 centimeters per year and reconstruct days that used to last 5 hours. Instruments turn deep time from abstraction into data. That shift matters. Once you see the moon not as a fixed ornament, but as a partner in an ongoing energy exchange, your identity moves too. You're no longer a spectator living on a static world under a permanent sky. You're part of a planet, mid-conversation with its satellite, both of them plugged into the wider gravity of the solar system, both evolving. Now, let's begin to sit with the scale of that. Every sunrise you watch, every tide that rolls in, every eclipse that goes viral online is a single frame in a film that's been running for billions of years. A film of energy being shuffled, orbits stretching, rotations slowing. We've only recently learned how to read that film, how to place our brief lives on a timeline where even the length of a day is a plot twist. The question is, what else in our fixed world is quietly sliding under the pull of deeper forces we've only just noticed? So now we can finally zoom out and compare the two pictures living in your head. On one side, the old textbook moon, a neat circle, a fixed distance, quietly orbiting in a flat diagram that never changes. On the other side, the version you've just built, a partner in a slow-motion dance, spiraling outward, powered by invisible tides that never stop tugging. Because here's what nobody tells you. That flat picture was never really wrong. It was just frozen. It was a single frame in a film where the camera had been paused for so long that you forgot it could move. You know the one. Earth here, moon there, a little number under the line between them, as if the distance were carved into the universe. Now let's begin to list what's actually hiding behind that line. First upgrade, tidal locking. The reason the same face of the moon always stares back at you is not a cosmic coincidence. It's the end result of eons of tidal friction inside the moon itself, slowing and synchronizing its spin with its orbit. Second upgrade, those tidal bulges Earth drags around, the lopsided oceans that are always trying to point at the moon, but never quite keep up. Third upgrade, friction. As Earth spins under those bulges, water scrapes along the seafloor and the coastlines, turning clean rotational energy into heat. Fourth, energy transfer. That drag steals a tiny bit of Earth's spin and hands it to the moon's orbit, letting the moon climb outward, centimeter by centimeter, year after year. It's literally orbital interest paid in tides. Then we layered in deep time, fossil corals and tidal rhythmites, acting as ancient clocks, showing that hundreds of millions of years ago there were more days in a year and each day was shorter. And on the other end of the timeline, lasers bouncing off Apollo reflectors, catching the moon in the act of escaping at 3.8 centimeters per year. From stone rings and rock to millimeter scale measurements in space, the same story repeats. So the moon's current distance? A snapshot. Our 24-hour day? A snapshot. Those spectacular, perfectly sized eclipses where the moon just covers the sun? Also a snapshot. In the long film of Earth-Moon history, we just happen to be sitting at the moment when all three line up in a way that looks designed. How long until that shot changes? Here's a test for your new model. Imagine explaining it to someone else in one breath. Earth spins, tides lag, friction heats, moon climbs. That's the chain. If you can see that sequence playing out in your mind, you've replaced the flat diagram with a living story. And yet, something is above the planets. Something is below them. This is now a tool you own. Whenever you see the moon, feel the tides, or even think about what a day means, you can drop this dynamic picture into place and ask a deeper question. What other orbits, what other clocks are quietly changing while we're not looking? So now we're back where we started. You're looking up at a moon that seems perfectly still, perfectly loyal, while in reality it's slipping away from you by 3.8 centimeters every year. The face never changes, the orbit looks steady, the tides come and go on schedule. And yet, quietly, the length of your day, the rhythm of your oceans, and the very shape of Earth's future are being rewritten in slow motion. Because here's what nobody tells you when you first draw that simple Earth-Moon picture in school. You know, the one with 2 circles, a neat little arrow, and maybe a few waves to show the tides. Emotionally, it feels like a childhood nightlight, always the same size, always in the same place in the sky. But once you follow the trail of fossil corals, counting hundreds of days in a year, and lasers bouncing off retroreflectors left by Apollo astronauts, that cozy image cracks open into a much more dramatic story. A slow, cosmic escape, powered by gravity and friction, measured in millimeters and millions of years. So, where does that leave you? You started with a comforting, almost flat cartoon of the moon's orbit. Now you're holding a dynamic, 3-dimensional timeline. A moon that once loomed huge when it was only tens of thousands of kilometers away. An Earth that spun so fast a day lasted barely 5 hours. And a far future where, in principle, both worlds could end up tidally locked, each showing the other just one face. It's the same system, same rock, same planet, different chapter. And yet, something is above the planets. Something is below them. Once you've seen how a single moon can stretch a day, stir an ocean, and slowly redraw an orbit, it's hard not to ask, what about all the other moons out there? How does Jupiter's crowded family evolve over billions of years? What happens on a planet like Venus with no large moon to tug at its spin? How does a changing star, swelling into a red giant, reach out with its gravity and rewrite every orbit in its grasp? Now, let's begin your next question. If this deep time perspective clicked for you, there's a whole web of stories waiting. How planets form in a rotating cloud and inherit their orbits. Why the solar system looks flat until you zoom out and see its full thickness. What ultimately happens to Earth, the moon, and every other world when the sun runs out of fuel. Each of those is another way of asking the same thing. How do orbits change while we're not looking? And here's the quiet truth beneath all of this. The reason we can spend time on these long, sprawling, slow-burn questions is because you're willing to follow them. Your curiosity, your comments, your decision to keep going past the simple diagram into the messy, 3-dimensional reality of space. That's the gravity holding up videos like this. So if you want to keep stretching this timeline to see how far the moon's story really goes once the sun starts to change, don't stop here. Because the next orbit we follow might make this one look simple. So if you want to keep stretching this timeline to see how far the moon's story really goes once the sun starts to change, don't stop here, because the next orbit we follow might make this one look simple. Here's the thought we want to leave you with. Tides are tiny, a few extra centimeters of water sliding up the beach, a faint bulge in the ocean you never see directly, a slow drag on Earth's spin you never feel. And yet, over billions of years, those almost invisible pulls have rewritten the whole relationship between Earth and the moon. Because here's what nobody tells you. The moon's great escape isn't powered by some dramatic shove. It's powered by repetition. Wave after wave, high tide after high tide, each one stealing a microscopic bit of Earth's rotation and slipping it into the moon's orbit. One more millimeter, one more distant night. Your actions here work the same way. A single like doesn't look like much. One comment feels small. One share is just a tap. But when you stack them together across thousands of people and thousands of nights, they change which stories rise like a spring tide and which sink below the horizon of the algorithm. So, let's start at the very beginning of that. Right now, while this is still fresh in your head, leave one trace behind. Tell us in the comments, what part of the moon's slow escape surprised you the most? Was it that it was once 20 times closer? That a day used to be only a few hours long? Or is it what you'll think about the next time you watch the tide climbing a flat stretch of sand?